Hello, chemistry. This is Ms. Hallowell. I'm going to go ahead and walk you through equilibrium, which is one of our last topics in chemistry this year. And I'm so excited for us to figure out what equilibrium means, what that means for chemical reactions, and how you're going to apply it to your homework. So I'm going to go ahead and jump right in. And we're going to start with a little bit of reflection, so some think time. So these three questions: what does equilibrium mean to you? Where have you heard the term equilibrium before? And are equilibrium and equal synonyms? Go ahead and take 30 seconds of think time. Think about your answers. All right, go ahead and stop that thinking. We're going to go ahead and look at some of those words that you might have come up with. So you may have come up with something like thermal equilibrium. You learned about that in physics last year. Maybe the word equal, which you may have seen in that third question. Balance is often a term that people come up with when they think of equilibrium or thinking about things staying the same. And so this last question I'm not going to address are equilibrium and equal synonyms, because I want you to try to discover that as we go through this PowerPoint. So it may be true for chemical equilibrium, but only circumstantially. So I want you to figure that out. All right, so we're going to jump into definitions. So equilibrium is a dynamic state, meaning a changing, dynamic versus static. Static means the same, staying the same. Dynamic means moving or changing. So a dynamic state in which opposing processes of change, so maybe opposing reactions, occur at the same time. So that means if you have a reaction, the reaction can be going from reactants to products, or it can be going from products to reactants. So it can go backwards. And we've never seen this before, at least not in chemistry. So what that means for equilibrium is when you get to equilibrium, or we get to some sort of state of equilibrium chemically, the rate of the reaction going from reactants to products, what we call the forward reaction, is equal to the rate of the reverse. So if you want, you can go ahead and write those down. Those are going to be important on your homework. All right, so we see a graph off to the right, and what I'm going to do is I'm going to pause on digesting that graph, and we're going to look at it further in one of the next few slides. So we're not going to look at it quite yet, we'll look at it soon. So when we represent a chemical equilibrium, we're going to go ahead and represent it with a weird symbol that you have not seen before. So the symbol looks like this. It's two half arrows, one pointing in the forward direction, which is this top arrow, and one pointing in the reverse direction, which is this bottom arrow. Both of these arrows together will replace that regular arrow that we're used to as a chemical reaction symbol. And what it means is that the reaction can go forward as normal, or it can go backwards. It would be the same idea as if you read a sentence forward and then read the sentence backwards. There are some sentences like that, or some words like that, like the word race car. You can read it forward or you can read it backwards. So what does chemical equilibrium actually look like? Well, if you look here, pretend this is a perfume. So we start and we spray the perfume on the left side of the room. Eventually, this perfume is going to diffuse or spread out, just as this is showing you right here. It's going to spread out so that it's equal around the whole room. Okay, and so once it's equal around the whole room, we're going to see that that's going to reach an equilibrium. However, when I say equal, I need to be careful with my words because I don't mean completely equal, and we'll get into that. So in this image right here, we see that, give it a second, it'll pop back. It starts in this one area and it's going to disperse. It's going to spread out until it's relatively even throughout this area. Notice that the molecules in this image are not stopping. Once they get to evenly spread out, they keep moving. They continue to be dynamic, which is the dynamic part of the term equilibrium, or the definition of equilibrium. So let's look at what that looks like when water evaporates. So if we look down here, let's not look up at this image yet. When we look down here, we can see that water is evaporating from the liquid state into the into the gas state in this closed flask. And let's notice that as time goes on, more of those particles start to evaporate and turn into a gas in the flask. However, we can also see that some of the particles are going back to being a liquid. And so once a certain number of particles have turned into a gas, and a certain number of particles are going back into a liquid, and those numbers are equal to each other, the rates of going from liquid to gas, and the rate of going from gas to liquid are equal, that's when you hit an equilibrium. So it doesn't mean that you have the same number of gas particles as you do water particles, right, or liquid particles. You can see that there's a lot more liquid here than there are gas particles. However, the rate of going back and forth is the same. And so that's where these graphs come in. So what I was just talking about is the amount. So let's look at the graph that says amount on it. The amount of these gas particles is way less than the amount of the liquid particles. So we notice that the amounts at the end are not the same. However, when you hit equilibrium, these amounts don't change. They're not equal to each other though, not necessarily. Right? In this scenario, they're not equal to each other. They could be, but it's rare. However, the other graph we're looking at is the rate of the reaction. So just as your new definition tells you, the rate of the forward reaction, once it starts to equal the rate of the reverse reaction, that's when you're going to hit an equilibrium. That doesn't mean that particles stop moving. It just means that the reaction, the forward reaction, is happening at the same rate as the reverse reaction. So quick note, I want you to note down in whatever notebook you're using right now, equilibrium does not mean you have the same number of reactants as you do products. So equilibrium does not mean the number of reactants equals the number of products. And that's very important. What's going to be equal at the end, so back to that word equal that we talked about on that first slide, what's going to be equal at the end is the rates of the two reactions. So notice that here we actually have a chemical equation. We're finally putting it into chemistry as we know it. So notice we used this arrow, this funky new arrow, in place of the arrow we used to use. The rate of the forward reaction, so going from left to right, is going to be the same as the reverse. So let's dive into this a little bit more. So this is the same reaction. I just gave it a couple boxes around them to indicate colors and as they're represented on the graphs. And so let's take a look at graph 1. In graph 1, we have time on our x-axis. So at time equals 0, at the start, this yellow line is at 0. That means we have none, the concentration, no yellow line. Well, what does that yellow line represent? Let's take a look. Oh, okay, up here. Yellow line represents the reactants. So at the beginning of the reaction, we have no reactants, no SO3. That means if we look up here, the beginning of the reaction, we have a certain concentration of the red line, which is our oxygen, and a certain concentration of the green line, which is our SO2. That means that we're starting with this side of the reaction, right? We're not starting with any of this SO3. We're not starting with what looks like the reactant in this equation. We are starting with the products, which means that if you start with the products and over time the amount of your products is decreasing, your reaction is going in the reverse direction. Your reaction is going towards the left. You're starting with this. You're not starting with any reactant, and you're going to shift towards the reactants. So my analogy here is a seesaw. If you take a look at this seesaw over on the left, you see that we're starting with the right side higher. That means that we're starting with more of our products. It means that our reaction is going to shift towards the left. So imagine you have like a baseball or soccer ball or basketball sitting right here. If you have more of your products than you do your reactants, and you put a basketball on here, even if you put it in the middle, it's going to roll towards the reactants. Whatever direction that basketball or soccer ball or whatever rolls is the direction the reaction is going to go. So notice here, I have more of my products. It's going to roll towards my reactants. That means my reaction is going to shift towards the left or towards my reactants, the reactants that I see on here. This graph shows the opposite. So if I look at graph number 2, I start with none of the red and none of the green, indicating that I start with no products. And I start with a lot of the reactants. So we're starting as we normally look at reactions. We're starting with only this side, and we're going to shift all the way. So we're going to see our yellow line decrease a little bit. We're going to shift. We're going to have less of this yellow than we did at the start, which is okay because that means our reaction is going towards the right. So if you take a look at the seesaw, you can see we start with more reactants than products. So if we put a basketball right in the middle, it's going to roll towards the products. That's the direction that this reaction is going to go, to the right. Now, we don't have seesaws in our house and little miniature seesaws to model this. So, well, if you have a seesaw in your house, that's pretty cool, but I don't. So what I use to model it is a pencil. So you can pick up your pencil, and I encourage you to do this right now. Pick up your pencil and put it against the seesaw to the left. So if you put your pencil against the seesaw to the left, you can see how if you place, say, because it's a pencil, you place a marble right in the middle of it, it'll roll off to the left because you have more products to start with. Whereas for graph number 2, take a look at those reactants. We have more reactants than products. We're going to have a different slant, the opposite slant on your pencil. Go ahead and put your pencil in that direction. If you put a marble on the center of it, it's going to roll towards the products. That's what you're going to end up with. All right, one more slide. So on this slide, I'm going to encourage you to answer these questions on your own. So I'm going to give you 30 seconds to answer these questions on your own. I will then give you what my take is on these 2 questions at the end, but I want you to have some think time first. So what is happening at the beginning of this image? What do you know about the concentrations of each compound? And which way is the reaction going before it reaches equilibrium? 30 seconds starts now. All right, so I hope you have an answer to those questions. For the first question, if you said that you're only starting with the products, you are correct. This is a review of what we did on the last slide. So we're only starting with the products. That means your concentration of the reactant, which is SO3, is 0. And you have high concentrations of the other 2. For the second question, which direction is the equilibrium going to be going in? Well, if you're starting only with your products, you can't go towards your products. You have to go towards your reactants to even it out. So you will go to the left. So that's a review of graph 1 from the previous slide. All right, let's take a look at what you will be doing. So you're going to go ahead and use the notes, use the information from this video. You're going to answer the questions on the document provided on Google Classroom, and you're going to upload a picture or pictures of your work to Google Classroom. As always, if it doesn't work that way, if something's not working right for you, just email it to me or text it to me. I prefer if you upload it to Google Classroom because then I can have them all in one place, but I don't want technology to stand in the way of you getting the credit that you deserve. So go ahead and hop on Google Classroom, upload a picture of your work to the Google Classroom assignment, use the textbook Showtime Lesson 3. So Showtime is the last chapter of, or sorry, the last section, the main section of the textbook. Lesson 3 is about equilibrium. Go ahead and use that if you have any more questions. And as always, use your pencil as a seesaw.